According to the National Electrical Code Section 250.122b, the size of the grounding electrode conductor, often abbreviated as EGC, must be based on the size of the service entrance conductor, also called SEC. The NEC stipulates that the EGC must meet one of two criteria. Firstly, it should be equal in size to the service entrance conductor if the service entrance conductor is 50 kcmil or smaller. Secondly, it should be equal to the size of the largest phase conductor if the service entrance conductor is larger than 50 kcmil. The interpretation suggesting that the EGC size can be based on the utility's service wires is incorrect according to the NEC. The NEC does not permit this practice. When facing similar issues in different jurisdictions, it's crucial to consult the specific electrical code adopted by that area. While the NEC is widely accepted, some regions might have implemented local amendments or unique interpretations. To effectively prepare for potential disagreements, gather the following details. Firstly, the NEC reference. NEC Section 250.122b clearly defines the requirements for sizing the grounding electrode conductor. Secondly, the local code reference. If the jurisdiction has adopted local code amendments, obtain copies of the relevant sections. Thirdly, expert opinion. Consult with a certified electrician or electrical engineer to gain their perspective on the code. Ensuring that the grounding electrode conductor is appropriately sized is vital for the safe operation of the electrical system. An undersized grounding electrode conductor can lead to a dangerous situation. Although the NEC doesn't allow sizing the grounding electrode conductor based on the utility's wire size, certain utilities might have their own specific requirements. It's essential to contact the utility company to determine if they have any unique stipulations. To provide a clearer understanding, let's delve deeper into the NEC requirements and provide practical examples. The service entrance conductor is the wire that runs from the utility's transformer to the service disconnect in a building. Its size is determined by the calculated load of the building, in accordance with NEC Article 220. Once the size of the service entrance conductor is known, the appropriate size of the grounding electrode conductor can be determined using NEC Table 250.66. This table provides the minimum size of the grounding electrode conductor based on the size of the service entrance conductor. For example, if the service entrance conductor is 2/0 copper, the grounding electrode conductor must be at least number 4 copper or 1/0 aluminum. It is important to note that this is the minimum size required by the NEC. In some cases, it may be necessary to increase the size of the grounding electrode conductor to meet local requirements or to provide additional protection. The grounding electrode conductor connects the service equipment to the grounding electrode system. The grounding electrode system consists of one or more grounding electrodes, such as a ground rod, a ground plate, or a metal underground water pipe. The purpose of the grounding electrode system is to provide a low impedance path to ground for fault current. This helps to protect people and equipment from electrical shock. The grounding electrode conductor must be securely connected to the grounding electrode system. The connection must be made in a manner that is approved by the authority having jurisdiction. In addition to the NEC requirements, some utilities may have their own requirements for grounding electrode conductors. These requirements may be more stringent than the NEC requirements. It is important to check with the local utility to determine if they have any specific requirements. The inspector's interpretation is incorrect based on the NEC, as it calls for sizing the grounding electrode conductor based on the size of the service entrance conductor and not the utility's service wires. In situations in other jurisdictions, it is critical to present your case using the NEC and other relevant documents. Prioritizing safety and ensuring proper grounding practices is always recommended. Let's consider a few examples to solidify the understanding of grounding electrode conductor sizing. Firstly, let's say we have a 200 amp service with 2/0 American wire gauge, abbreviated AWG copper service entrance conductors. According to NEC Table 250.66, the minimum size for the grounding electrode conductor would be number 6 AWG copper or number 4 AWG aluminum. Secondly, suppose we have a 400 amp service with 500 kc mil copper service entrance conductors. Using NEC table 250.66, the minimum size for the grounding electrode conductor would be 1/0 AWG copper or 3/0 AWG aluminum. Thirdly, imagine a 100 amp service with number 4 AWG copper service entrance conductors. In this case, the grounding electrode conductor would need to be at least number 8 AWG copper, as per NEC table 250.66. These examples illustrate the direct relationship between the service entrance conductor size and the required grounding electrode conductor size, as mandated by the NEC. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, tripping the circuit breaker or fuse and preventing electrical shock. Bonding connects all non-current carrying metal parts of the electrical system, such as metal conduit, enclosures, and equipment frames, to create an equipotential plane. This helps to minimize voltage differences and reduce the risk of electrical shock. The grounding electrode system must be properly installed and maintained to ensure its effectiveness. Ground rods must be driven deep enough into the ground to make good contact with the earth. Ground plates must be buried below the frost line. Metal underground water pipes must be bonded to the electrical system. Regular inspections of the grounding electrode system are recommended to ensure that it is in good condition. Any damaged or corroded components should be replaced immediately. In addition to the grounding electrode conductor, there are other important grounding and bonding conductors in the electrical system. The equipment grounding conductor, often called EGC, connects the non-current carrying metal parts of equipment to the grounding system. The equipment grounding conductor provides a low impedance path for fault current to return to the source. The bonding jumper connects the neutral conductor to the equipment grounding conductor at the service entrance. The bonding jumper ensures that the neutral conductor and the equipment grounding conductor are at the same potential. The size of the equipment grounding conductor is determined by NEC table 250.122. This table provides the minimum size of the equipment grounding conductor based on the size of the overcurrent protection device protecting the circuit. The bonding jumper must be sized in accordance with NEC section 250.28. This section provides the requirements for sizing the bonding jumper based on the size of the service entrance conductor. Improper grounding and bonding can create dangerous electrical hazards. Electrical shocks, fires, and equipment damage can result from faulty grounding and bonding practices. It is essential to follow the NEC requirements and to use qualified electricians to install and maintain electrical systems. Grounding electrode conductors are typically made of copper, aluminum, or copper-clad steel. Copper is the most common material used for grounding electrode conductors due to its excellent conductivity and corrosion resistance. Aluminum is a less expensive alternative to copper, but it is not as conductive and is more susceptible to corrosion. Copper-clad steel combines the strength of steel with the conductivity of copper. Grounding electrode conductors must be protected from physical damage. They should be installed in conduit or otherwise protected from impact and abrasion. Grounding electrode conductors must be continuous and without splices. Splices can increase the impedance of the grounding path and reduce its effectiveness. Grounding electrode conductors must be securely connected to the grounding electrodes. The connections must be made using approved connectors and methods. Grounding electrode conductors must be accessible for inspection and testing. The location of the grounding electrode conductor should be clearly marked. The NEC provides detailed requirements for grounding and bonding electrical systems. It is essential to understand and follow these requirements to ensure electrical safety. If you have any questions about grounding and bonding, consult with a qualified electrician or electrical engineer. Let's discuss some common misconceptions about grounding and bonding. Firstly, some people believe that grounding is only necessary for safety. While safety is a primary concern, grounding also helps to improve the performance and reliability of electrical equipment. Secondly, some people think that grounding is the same as bonding. Grounding and bonding are related but distinct concepts. Grounding provides a path for fault current to return to the source, while bonding connects all non-current carrying metal parts of the electrical system. Thirdly, some people assume that the ground rod is sufficient for grounding an entire electrical system. A single ground rod may not provide adequate grounding for a large or complex electrical system. Multiple ground rods or other grounding electrodes may be required. Fourthly, some people believe that the grounding electrode conductor can be any size. The grounding electrode conductor must be sized in accordance with NEC Table 250.66. Using an undersized grounding electrode conductor can compromise the effectiveness of the grounding system. Fifthly, some people think that the equipment grounding conductor is only necessary for sensitive electronic equipment. The equipment grounding conductor is required for all electrical equipment, regardless of its sensitivity. Sixthly, some people assume that the neutral conductor is the same as the equipment grounding conductor. The neutral conductor carries current under normal operating conditions, while the equipment grounding conductor only carries current during a fault. Seventhly, some people believe that GFCI, ground fault circuit interrupters, protection eliminates the need for grounding. GFCI protection provides additional safety, but it does not replace the need for proper grounding. GFCI devices detect ground faults and interrupt the circuit, but they do not prevent ground faults from occurring. Eighthly, some people think that surge protection eliminates the need for grounding. Surge protection devices protect equipment from voltage spikes, but they do not replace the need for proper grounding. Surge protection devices rely on a properly grounded system to divert surge current to ground. Ninthly, some people assume that if an electrical system is working properly, then the grounding is adequate. The grounding system may be inadequate even if the electrical system is functioning normally. Regular inspections and testing of the grounding system are necessary to ensure its effectiveness. Tenthly, some people believe that once a grounding system is installed, it never needs to be maintained. Grounding systems can degrade over time due to corrosion, damage, or other factors. Regular maintenance is necessary to ensure that the grounding system remains effective. Finally, let's address the importance of documentation and record keeping for grounding systems. Accurate documentation of the grounding system, including the location of grounding electrodes, the size and type of grounding conductors, and the results of grounding tests, is essential for future maintenance and troubleshooting. Records should be kept of all inspections, tests, and repairs performed on the grounding system. This information can be invaluable for identifying potential problems and ensuring the continued effectiveness of the grounding system.